Hello, this is a little short video talking about intermolecular forces, not including hydrogen bonding or dipole-dipole. Again, let's just kind of recap here a little bit. We have the idea that we have a molecule, and if that molecule doesn't have a charge, then it would have no reason for it really to interact with another water molecule, okay, or any other molecule, let's say it has to be water. We call that intermolecular force. So this particle would be more likely to kind of go its own separate way, and this guy go its own separate way, looking at things like gases. Okay, but if we have a situation where a molecule does contain a positive area and a negative region, then there's a good chance that it will attract to another molecule that also has these, and they'll attract via intermolecular forces. We call it IMFs. There are a few different type of intermolecular forces, and we've discussed these in detail in other videos. The main one would be what I would call hydrogen bonding. Okay, now that would require, or another subset of that would be dipole. Both of these are where you have a highly electronegative atom, nitrogen, oxygen, fluorine, bound to some other element. If that happens to be hydrogen, then we have hydrogen bonding. Otherwise, we call it dipole-dipole. Now, if we don't have a nitrogen, oxygen, and fluorine, then we don't have what we call a polar bond. And we went through a whole series of checklists on previous discussions about, okay, polar bonds, and then symmetry, okay, and whether it be no polar bonds, yes, you're symmetrical, and both of these cases would be non-polar. Well, so the basic idea here is like, okay, if I don't have one of these guys, is it ever possible for me still to have some sort of intermolecular force? And the answer is yes. So there is another type of intermolecular force, and this is called London forces. Okay, so for example, if we see a compound, let's say fluorine, put those over here, F2. Let's go with Cl2, Br2, and I2. So here are all these halogens. And you'll note that in real life, this one is a gas. This one, gas, liquid, and very easily could be a solid. So for some reason, molecules of fluorine, there's almost no interaction between the two. Whereas chlorines, we start to get a little bit of interaction, and then bromines, we get lots of interaction. And iodine crystals have, oodles of interaction in the sense that they form a solid. So we have gas slash liquid, and then a solid. Okay, so there has to be something going on between this particle here, the nucleus, electrons spread around. Okay, that somehow we're getting some Coulombic attractions between these guys. So as always, scientists kind of look at what's happening in nature and they backtrack to see, okay, well, what could be going on, and could I come up with a theory or possibly about how this might work? And here's what we call, here's kind of how we figured this, that and it's not just with this family, it's all over the place, these things happen, is that electrons can be called polarized. That might be how you spell it, where we have an atom which has electrons around the outside, and because they're able to move, and the nucleus can't, we could get a situation where more electrons might end up on one side versus another. Okay, which give this a relatively negative and relatively positive. Now, it's often thought that this was called induced charge, because you could have something that's negative come up along here and push away electrons via electromagnetic and push away and create a positive dipole. So that's the word induced. You'll see that occasionally. But either way, every atom, because every atom has electrons, okay, every atom has the ability, okay, to have London forces. There are some factors that would cause an atom's ability to become magnified, meaning they really cause lots of dipoles, okay? And the first one is going to be number of electrons, okay? And you increase the number of electrons, you increase the opportunity for this polarization, or London forces. And this is what's happening in these guys. So a question might be is, okay, you'd say, well, okay, why is iodine a solid whereas fluorine is a gas? That's an important question to answer, and the reason why is because iodine has more electrons, therefore it's more easily polarized, and therefore we get small dipoles forming. What's up?
You are here. I'm going to do a pogo this week. Are you in?
So it is more polarized, and then therefore tracks one item to another. So in a sense, number of electrons is very important. Now what you can't do is say, okay, bigger mass. This is not an option. Okay, not an option. Bigger mass. So you must say more electrons, increase London forces. Next, we have long chains. Okay, long chains essentially have an opportunity here for lots of surface area. Okay, so we have increased surface area. Okay, increased surface area means that more, it's like a Velcro. These positives and negatives, they aren't really all that big. They're not really all that strong. So if we could find some way to multiply them, it really helps out. So we have a long carbon chain, generally that's how this work, and we get a positive and over on this side and a negative over here. Okay, then maybe we can get another one of these guys. It might stick. Positive on this side, carbon chain, negative here, and we get a little bit of sticking to occur. But if I get a long chain of carbons, then I have a much greater opportunity for these guys to legitimately stick together. Okay. So long chains really amplify London forces. So whenever you look at a molecule, as far as intermolecular forces are concerned, you always want to be able to analyze this and say, okay, what type of intermolecular forces are present? We have options for hydrogen bonding. We have options for dipole, and we have London forces. So if we look at a molecule, let's say for example ammonia NH3, we'd want to be able to take this thing and sort of sketch out what it looks like. Okay, this is a molecule, and we have an unbonded pair here. So we're following along with a trigonal pyramidal. Okay. And as I look at this, I'm saying, okay, well, these two both the same thing essentially. But because we have our highly electronegative atom, nitrogen, oxygen, fluorine, then this is looking like we're going to be sliding into the hydrogen bonding category because this thing is polar bonds, it has polar bonds, and we are also asymmetrical. You'll note that this thing is following the trigonal pyramidal shape, polar bonds, so we are polar. And I would expect this thing to have properties of polar molecules. If we looked at another one, you'd say, okay, well, what about, let's say, let's go with hexanol. Okay, let's just give it a unique compound. 1, 2, 3, 4, 5, 6, 7, and then an OH on the end, hexanol. So 1, 2, 3, 4, 5, 6, 7. So that'd be heptanol with a 7. Either way, what does this thing distinguish about it? Well, we have a long chain, which of course is going to be indicating some amount of London forces. And of course here we have a possibility for a hydrogen bond. You should be able to look at a molecule and say, what do we have and what is available? The more intermolecular forces you have, the more likely you're going to be experiencing attraction to other molecules. Okay? All right. Thank you very much.